The concept of MRGP are given in next two definitions. The first definition, a sequence of bivariate random variables yn, sn is called a Markov renewal sequence or Markov renewal process. S naught is equal to 0. In this example also we made it S naught is equal to 0. Sn plus 1 is greater than or equal to Sn, and yn is belonging to omega dash, where omega is the state space, omega dash is the subset of omega. For all n greater than or equal to 0, the yn, the conditional distribution of yn has to satisfy this property. The first line, the probability of yn plus 1 is equal to j with the difference of time instants is less than or equal to t, given that the system was in the state, some state at y naught at the time instant s naught, till the system was in the state I at the time instant Sn. This conditional distribution is same as the conditional distribution with the only the latest information. The probability of yn plus 1 is equal to j, the difference of regeneration time points is less than or equal to t, given only yn is equal to I. That means the conditional distribution depends only the current information or latest information, not the complete history. So that is nothing but the Markov property. Next, that is same as the conditional distribution of instead of yn to yn plus 1, you can find out the distribution of y naught to y1. Because of it is a time invariant, because of it is a time homogeneity, this conditional distribution is same as probability of yn is equal to j. The first regeneration time point is less than or equal to t, given that y naught is equal to I. So that means the conditional distribution depends on the current state, not the past history, including the time homogeneous property. Then that is the way we define the bivariate random variables, that is yn, sn satisfies this property. Then the MRGP is defined as follows. A stochastic process z of t with the state space omega is called a Markov Regenerative process if there exists a Markov renewal sequence yn, sn such that all conditional finite dimensional distribution of z of sn plus t given z of u, where u is lies between 0 to sn, yn is equal to I, are the same as those of z of t given y naught is equal to I. So this is the probabilistic replica. The stochastic process z of t is said to be a Markov regenerative process if all conditional finite dimensional distribution of z of sn plus t given all the past history till sn including yn is equal to I, that is same as the distribution of z of t given y naught is equal to I. That means it includes the time homogeneity as well as the Markov property. Note that the above definition implies that z of sn plus n plus or z of sn minus is a embedded discrete time Markov chain or just a embedded Markov chain in z of t. Also, Sn is the stopping time or regeneration points. Stopping time is nothing but the Markov property is satisfied at those time points for the given stochastic process. So, in this example, before the arrival occurs, Z of Sn minus is a embedded discrete time Markov chain just before the arrival occurs. Will be a embedded Markov chain in this example. The way we discuss the semi-Markov process with the transition probability matrix and the Sojourn time distribution, here we have to explain the global kernel and the local kernel. So, that we are going to discuss now. We denote the conditional probability in the equation number 2 by ki of j of t. Equation number 2 is nothing but the conditional distribution of yn plus 1 is equal to j with the difference of time regeneration times are less than or equal to t, that is same as because of Markov property and the time homogeneous property, this is the probability of yn is equal to j, comma s1 is less than or equal to t given y0 is equal to I.
A Markov renewal sequence is also defined in the bivariate as this, and usually this form of definition is frequently used since renewal time and the state of the time and the state of the system at renewal instant both are important.
So, this conditional probability becomes the transition probability, that is this conditional probability will form a matrix K of t, and that is called a global kernel of the Markov renewal sequence. For the Markov renewal sequence, we can find the global kernel, and the global kernel is the matrix K of t that consists of K of I comma j of t, where each K I comma j of t is nothing but probability that P of y1 is equal to j with s1 is less than or equal to t given y0 is equal to I. Now, we are going to discuss the local kernel. That is also a matrix that consists of E of I comma j of t, where I is belonging to omega dash and j is belonging to omega. Omega dash means the collection of states at which the time transitions of the system satisfies the Markov property at those time instants, those collection of states forms the omega dash, and that is a subset of omega. So, E of I comma j of t is nothing but what is the probability that the system will be in the state j with the first regeneration time point is going to be greater than t. That means the system will be in the state j after the time t, the first regeneration going to occur after time t. The system will be in the state j at the time t given it was in the state I at the previous regeneration time point, or at S0 the system was in the state I. So, this will form a local kernel. So, using global kernel and the local kernel, one can find the steady state and the transient behavior of Markov regenerative process. Now, we are going to discuss the limiting distribution or steady state measures. We studied the limiting behavior of the MRGP by taking limit as a t approaches infinity. We require two new variables to be defined, namely the mean time alpha I comma j of the MRGP spends in the state j between two successive regeneration time instants, given that it started in the state I after the last regeneration. So, this is nothing but the average spending time in the state j, given that it was in the state I at the last regeneration. So, alpha of I comma j is nothing but the expectation of a time in state j during the interval 0 to S1, where S1 is the first regeneration time instant, given that the system was in the state I at the previous or last regeneration time. And the steady state probability vector V of the embedded Markov chain. That means V is equal to Vp and the summation of Vk's are is equal to 1, where k is belonging to omega dash, and the P is the one step transition probability matrix of embedded Markov chain. So, from the global kernel k, that is a k of t. If you make a t tends to infinity, you will get the one step transition probability matrix P. So, from using P, you can get the steady state probabilities V by solving V is equal to Vp and the summation of Vk is equal to 1. Once you solve this using the alpha ij, you can get the limiting distribution. So, the limiting distribution is given in the following theorem. Let z of t be the MRGP with the Markov renewal sequence yn comma Sn. Let nt denotes the total number of states changes by time t. Then the sample path of zd are right continuous with the left limits, and the n of t is a semi-Markov process. The y of n of t is a semi-Markov process which is irreducible, aperiodic and positive recurrent, and V is a positive solution to the equation 4, that is this one, summation of Vi is equal to 1 and V is equal to Vp. If these properties are satisfied, then the steady state probability vector pi, whose elements are pi j's, that is nothing but the limit t tends to infinity, probability of z of t is equal to j, using this formula where bk's are nothing but the summation of alpha k's. So, as long as these three properties are satisfied, that means the sample path has to be right continuous and the semi-Markov process has to be irreducible, aperiodic and a positive recurrent, and you need a positive solution, the steady state probability vector, then you can get the steady state probability for the Markov regenerative process